We are on AP Review FRQ topic number 9 out of 10 topics. So we have one more to go after this. This one is on polars. Okay, so in polars, we're going to review just for a moment before we get to some of the FRQ examples that I have. In polar equations, we are given an equation in the form r is equal to some function of theta, right? So maybe it's r is equal to 3 sine theta, or maybe it's r is equal to theta cosine 2 theta. Whatever, there's some function of theta and r is equal to that function of theta. Okay, so we have a couple of different formulas that we need to know. The first is for the area inside of a polar curve, or a part of the polar curve. For area, it's an integral, and we go from theta 1 to theta 2, however you want to denote that. You can do a to b. Oftentimes, since we're dealing with an angle of theta, oftentimes we'll do an alpha to beta, but either, whatever, however you want to denote that. This is your first theta value to your last theta value. And inside the integrand part, it comes from the area of a sector if theta is in radians, and the area of a sector is 1/2 r squared theta, but our theta will be d theta because we just have a little slice of theta here. So keep in mind what that means. If we have this, let's say we have this limacon, and if we have the integral from 0 to 2 pi, that means we're starting at theta is 0, and theta goes around the entire polar coordinate plane here, and we go all the way to 2 pi. So the first little theta slice will look like that. That's our first little d theta, and then it keeps going around, and we'll go all the way around, and we'll get back to 2 pi, right? And then this will be 1/2 r squared d theta, and that would give the area of the entire interior area of that curve. So this is something we need to know. Okay, 1/2 r squared d theta. Don't forget the 1/2. It's part of the area of a sector. It's the area of one of these little sectors. Okay. All right, so we have area. The next thing we need is we would like to be able to find the slope of the tangent line to that curve. The slope of the tangent line. Sometimes it's negative, sometimes it's positive. So the slope of that tangent line. To get the slope of the tangent line, we need to remember that slope is always dy dx. Always dy dx. The problem here is that we have r as a function of theta, and how do we get dy dx out of r being a function of theta? And the answer is we know two little pieces of information. Y is always equal to r sine theta, and back in this unit we saw why that is true, but y is equal to r sine theta. So we can replace r with that whatever function of theta you have, and x is always equal to r cosine theta. Okay, so if you want dy dx, the slope, if you want the slope of the tangent line to that curve, it'll be dy dx, but we can write that parametrically, dy d theta over dx d theta. And now you can take replace r with your function of theta, right? And then you can find dy d theta and dx d theta, and that would give you that. Okay, and we'll be doing that in some examples. Okay, the last thing we need to talk about before we get to the examples is we do have r as a function of theta, and the question is, what is drd theta? It's not the slope of the tangent line, but what is it? It does have meaning, and here's the meaning. Let's pull back up that little limacon. Okay? If we start theta at 0, as theta increases, so as theta increases, it goes around here, as theta increases, Drd theta is the rate of change of r with respect to theta. So r starts off whatever value that is. Let's say that that's a 2 for the sake of giving me a number. Let's say r starts off at 2. When theta is 0, r is 2, let's say. As theta increases, r gets further away from the origin, right? R gets further away from the origin until we get to some value, and I don't know where that is here, it's hard to tell by my picture, but until we get to some value, and then it will start to get back closer to the origin, right? So Drd theta, that's what it talks about. Is r increasing? Is it getting further from the origin? Or if Drd theta is negative, that would imply that r is getting closer to the origin as it goes around. Okay? So Drd theta evaluates what r is doing with relation to the origin. Okay? The distance between the curve and the origin, is that increasing or is that decreasing? So we'll keep that in mind when we're doing any of these FRQs. Okay, let's get to some problems to go over. Okay, the first one we're going to do is the problem from 2018. This was number 5, no calculator, and the fact that it's no calculator doesn't bother me at all. It just means that we're going to have a lot of write an expression involving an integral instead of actually solving that expression. Okay? So let's take a look at this problem. The graphs of the polar curves r is equal to 4 and r is equal to 3 plus 2 cosine theta are shown in the figure on the right. It's going to be good if we know something about these curves, if we can distinguish. We don't have a calculator. Can we distinguish which curve is which? So this goes back to what you learned in pre-cal and what we reviewed in this unit. R equals 4 is a circle centered at the origin of radius 4. So find that circle centered at the origin. This is r is equal to 4. That's that equation. The other one is a limacon with no loop, bumped out on the positive x-axis because I see the positive cosine. So the other one is this limacon with no loop. Okay? Now, they tell us that the curves intersect at theta equals pi over 3 and theta equals 5 pi over 3. If they didn't give us that, we would have to go and find that. Okay? They were kind enough to give that to us, though. If we weren't given it, to find these intersection theta values, we would set the two r's equal and solve for theta. And it wouldn't be too hard. You need to know a little trig. So these theta values are important. I'm going to sketch these in. This is theta equals pi over 3, and this is theta equals 5 pi over 3. Part A. Let R be the shaded region inside the graph of r equals 4 and also outside of the graph of r equals 3 plus 2 cosine theta, as shown in the figure on the right. Write an expression involving an integral for the area of R. Okay? So we know what our formula for area is. So it's going to be an integral. So this area, this shaded region, we need the integral to begin at theta equals pi over 3, right? And go around. Remember, we can only go in the positive direction, so we're going to always be going clockwise, right? So begin at pi over 3 and end at 5 pi over 3. You wouldn't want to begin at 5 pi over 3 and go to pi over 3, because then you'd get a negative answer. Okay? All right. Now, if I look at this, now to focus on the integrand, I know I need 1/2 r squared, right? But we have 2 r's, and so let's think about this. I need the outside r to be my outer radius, and then I need to subtract out this piece because I don't want any of that white space in there. So it'll be 1/2 of this r squared minus 1/2 of this r squared. That's the piece I don't want. So 1/2 of that 4 squared minus 1/2 of the other r squared d theta. And that will give me that, that shaded area. We could write this in two different integrals too. Just the integral of 1/2 4 squared d theta minus the integral, same boundaries, of 1/2 of this r squared d theta. Okay, that would also give it to us. Okay, part B. Find the slope of the line tangent to the graph of this curve at theta equals pi over 2. So slope is dy dx. Slope is dy dx. In a polar curve, that's dy d theta over dx d theta. So we need y as a function of theta and x as a function of theta. So y is always equal to r sine theta, right? That means for our case, y is equal to 3 plus 2 cosine theta sine theta. And I can find dy d theta from that. X is equal to r cosine theta, so x is equal to 3 plus 2 cosine theta times cosine theta. Okay? All right, let's come over here and find dy d theta. So here's my y equals. I'm going to be using the product rule there. The derivative of 3 plus 2 cosine theta, the derivative of 3 is 0. The derivative of 2 cosine theta is negative 2 sine theta. So negative 2 sine theta times that sine theta over here. And then plus, now I'm leaving the parentheses alone, and I'm multiplying by the derivative of sine. The derivative of sine is cosine. That takes care of dy d theta, and now I need dx d theta. So again, the derivative of this term is negative 2 sine theta multiplied by the cosine theta plus, now I'm leaving the parentheses alone, and I multiply by the derivative of cosine. The derivative of cosine is negative sine, right? So I'm going to come over here and change this plus to a minus and make that sine. Okay? So I found dy dx as a function of theta, so now I just need to plug in theta equals pi over 2. And a safe stop spot here, I'm communicating what I'm doing. I'm plugging in pi over 2. A safe stop spot would be simply to rewrite this entire thing with pi over 2 in for theta. That would be a safe stop. Okay? But I'm pretty confident that I know what sine of pi over 2 is and cosine of pi over 2 is, so I'm going to go ahead and put numbers in, but know that you can totally safe stop putting pi over 2 in. Okay, sine of pi over 2 is 1. Sine of pi over 2 is 1. So I have negative 2 times 1 plus 3 plus 2 times 1 times cosine of pi over 2, and cosine of pi over 2 is 0. All over negative 2 times 1 times cosine of pi over 2 is 0 minus 3 plus 2 sine theta. Wait a second. I think I wrote that wrong. I did write that wrong. I copied this down wrong. This was a cosine theta. This was a cosine theta, right? I just copied it down wrong. So that's going to change this to a 0 here. Not that it'll matter because I'm writing a 0 there, but that's going to be a 0 here. This will be a 0 here, and then this will be a 1 from that. Okay? Now this would also be a safe stop spot, okay, unless this is undefined. And if this is undefined, then we need to write undefined instead of just boxing this, right? This is not undefined though, because I know the denominator is not going to be 0, and the numerator is not going to be 0, so I could just stop here. But of course that would be a -2 on top, and we would have a -2 on the bottom. We'd have a -3 on the bottom, so this would be 2/3. Okay, I do advise you to safe stop though. Don't take a chance of adding or subtracting wrong and lose your credit. Okay, for part C, a particle moves along the portion of the curve, just this one curve, for theta between 0 and pi/2. Okay, the particle moves in such a way that the distance between the particle and the origin, that's r, you guys. It's the distance. It's actually the absolute value of r, right? The distance would be absolute value of r, but in our case, r is always positive for this curve. It's always positive, but we're only looking for between 0 and pi/2 anyway. So r is positive, so the absolute value of r will be just r for us here. Okay, they're saying that that increases at a rate of 3 units per second. So they're giving us dr dt is 3 units per second. Okay, we want to find the rate at which the angle theta changes with respect to time at the instant when the position of the particle corresponds to theta equals pi/3. So we're looking for d theta dt at the instant when theta equals pi/3. Okay, and indicate units of measure. I'm going to bubble that in hopes that I don't forget it at the end. Okay. All right, so we're given r is equal to 3 plus 2 cosine theta. We want to find d theta dt. So I'm going to write down my equation. Okay, and I need to take the derivative of both sides with respect to t. Because I have dr dt, I want d theta dt. So on this side, the derivative with respect to t of r is 1 dr dt. The derivative of 3 with respect to t is just 0. The derivative of 2 cosine theta with respect to t is -2 sine theta times d theta dt. It's a little chain rule in there. So chain rule, we first take the derivative with respect to theta, and then we multiply by d theta dt. Okay? And now we're going to plug in theta equals pi/3. So when theta equals pi/3, communicate what you're doing. Theta is pi/3 now. dr dt is 3. It's sine of pi/3. d theta dt. And a safe stop spot would be just to divide both sides by -2 sine of pi/3. And that would be a safe stop spot, okay? So I advise you to safe stop when you can. Now I do indicate units of measure, d theta dt. So we need units of theta divided by units of time. Theta, remember, is in radians for us. Time, in this case, is in seconds. So those are the units. And let's take a look at how this was stored. In part A, this little area part, it was 1 point for the constant and the limits. The constant is the 1/2, the limits are the boundaries on the integral. And I'm sorry, 2 points for the integrand, so everything else in the integral. The 4 squared minus the other r squared and the d theta. Don't forget your d theta, okay? So all were 3 points. For part B, there was 1 point awarded for your dy d theta, and they wrote this out: drd theta sine theta plus r cosine theta, or the one for dx d theta. Drd theta cosine theta minus r sine theta. Okay, so 1 point if you got either one of those right. That would be the top or the bottom. Okay. 1 point for your expression for dy dx. So 1 point for the entire thing here. And they wrote that out. They wrote this over this. Okay. I don't know that I want to rewrite all that, but that over that, same thing. Okay. And then 1 point for the answer. So 3 points. And then part C was also worth 3 points. 1 point for dr dt is equal to dr d theta times d theta dt. That was our little chain rule here. So that's dr d theta, and this is d theta dt. Okay? 1 point for d theta dt is equal to dr dt times 1 over negative 2 sine theta. So I did that right here, right? I did that right here after I plugged in pi over 3 for theta, so that's fine. And then 1 point for the answer with units. So next up, I'd like to take a look at the FRQ from 2014. This is the one from 2014. It was number 2, so this one was with a calculator. Okay. So I'm going to grab my calculator, take a second to clear out anything that's in there. Okay. Alright. So remember on these, you guys, when you have a calculator, when you have access to a calculator, that's fine, but only use polar mode if you don't know what the graph looks like. If you know what the graph looks like, there's no reason to go and use polar mode. Stick with function mode, okay? All right, the graphs of the polar curves r is equal to 3. We know that's a circle centered at the origin with radius 3. And r is equal to 3 minus 2 sine of 2 theta. This is not one of our known named curves from pre-cal, okay? So this is some kind of a funky curve. So here we have, they're only shown from 0 to pi. Clearly they're only shown from 0 to pi. So here we have the r is equal, this is r is equal to 3. And then this funky one is r is equal to the other. 3 minus 2 sine 2 theta. Okay? All right. Let R be the shaded region that is inside the graph of r equals 3 and inside the graph of the funky curve. Find the area of R. Okay? So if you look at this, the shaded area, if I just look in the first quadrant, the shaded area is only dependent on that funky curve, right? It's only dependent on that curve. I don't even need this out here to get the area of that shaded part. If I look from pi over 2 to pi, it's just the opposite. All I need is this area of that quarter of a circle. The other curve does not matter at all for that area. So it's clear to me that I need to split this up into 2 integrals. I need the integral from 0 to pi over 2. And then I only need this funky curve. So remember, it's 1/2 of that r squared. So 1/2 of that r squared d theta. And then I'm going to add to that this other area, right? Now I could write this area as an integral, but I also know that it's 1/4 of a circle with radius 3. So I'm just going to do it as 1/4 pi r squared, where r is 3. But know that you could have done that with an integral too. Okay, and it says to find the area, not just write the integral that gives the area, but find the area. So we actually have to go and find it. I am going to, since I have this whole FRQ, I'm going to put this in for my y1. This r is equal to 3 minus 2 sine 2 theta, where my x is representing theta here. That will allow me to use that all throughout the problem, okay? I don't really have to go put 3 in, but you could if you wanted to, okay? So now that I have that in there, for this integral, math 9, 0 to pi over 2 of 1/2. This is just my y1, right? So y1, I didn't need that parentheses here, but since I started it, I'm going to close it up. D theta, okay, plus, and this is 9 pi over 4, right? So 9 pi over 4. So 9.708 or 707, right? So 9.708. I like to round those, okay? That part was worth 3 points. That was worth 3 points. So 1 point for the integrand, 1 point for the limits, and 1 point for the answer. I'm guessing that they're talking about the integrand only for this one. You could have totally done it for this one as well, okay? It would go from pi over 2 to pi. All right. Part B. For the curve r is equal to 3 minus 2 sine of 2 theta, that's the funky curve, find the value of dx d theta at theta equals pi over 6. So we just need dx d theta. We don't need the entire slope. They're not asking for the entire slope. They're only asking for dx d theta. So we know that x is equal to r cosine theta. So for us, r is equal to 3 minus 2 sine of 2 theta times cosine theta. Yeah? So we need dx d theta at pi over 6, and we have a calculator. So I'm going to let my calculator do this. We could do it by hand using the product rule again, but I'm going to just let my calculator do that work. Okay? So I need the derivative of this. I need the derivative of that, right? So math 8 for derivative with respect to x, because x is representing theta for me. This is my y1, and I need to multiply by y1 by cosine theta. And we're going to evaluate that at pi over 6. So negative 2.366. Okay? Part C. The distance between the two curves changes for theta between 0 and pi over 2. Let's take a look at what they're talking about. The distance between the two curves from theta is 0 to theta is pi over 2. So up here at our picture, from 0 to pi over 2, yes, there is a distance between the two curves, right? At first, at theta equals 0, that distance is 0. At theta equals pi over 2, the distance is 0, but between there, the distance between the two curves, think of it as drawing a line from the origin out, okay? So that distance here does indeed change as we go along the curve, right? As theta increases, that distance also increases. Okay? So this distance is changing. Find the rate at which the distance between the two curves is changing with respect to theta. So I need, first of all, I need to get an expression for that distance. I'm going to call it d, and I'll say that down here. I'm going to call it d. D is going to represent the distance between the two curves. So up here, this is d, the distance between the two curves. D is going to be the outer minus the inner curve. Okay? Think back to when we did area and volume and we had like top minus bottom or right minus left. Well, in polar, you need to do outer minus inner. Kind of makes sense. So D is going to represent the distance from the outer to the inner curve. So let's state that. I'm going to let D equal the distance from the outer curve to the inner curve, which is the distance between the two curves. So D will be the outside is the r is equal to 3, and the inside is the funky curve. So 3 minus that funky curve. Don't forget to use parentheses around that. Okay. I can leave it like that, but I'm going to go ahead and distribute that negative through, and 3 minus 3 is going to be 0, and then I'll just have that be 2 sine of 2 theta. Make it just a little bit easier to put in my calculator. Okay. I want the rate d is changing, so I want d distance with respect to theta. So they'll tell you what it's with respect to. So here's my d. I just need to take the derivative with respect to theta at pi over 3. So again, we could easily do that by hand, but I'm going to go ahead and let my calculator do that work. So I need the derivative of 2 sine of 2 theta, which is x for me, at theta equals pi over 3. Okay, so our calculator gives us this. I would totally round this to three decimal places, which would be -2, but know this, your calculator always uses a numerical method to evaluate these derivatives and integrals, and sometimes there is a noticeable error in that numerical method that the calculator uses. So this time there is definitely a noticeable error, because if we did this by hand, we would get -2, period. We would not get this weird number, right? So know that your calculator uses a numerical method so that you can write the appropriate value when you see something like this. So this is just -2. Okay, I started telling you how much these were worth. Let me go back and do this. This one right here was worth 2 points. 1 point for the expression for distance, and 1 point for the answer. 2 points. Part B up here, that was worth 2 points. 1 point for the expression for x. That was this thing here, the expression for x, and then 1 point for the answer. Okay, one more part to this problem. Part D. A particle is moving along the curve. So notice that in these last two problems, they included a parametric, a motion of a particle within these problems, within this polar problem. Okay. It's not uncommon for them to do that. They've been doing that recently. Okay? A particle is moving along that funky curve again, so that d theta dt is 3 for all times. Find the value of dr dt at theta equals pi over 6. Okay, this is just a little related rates problem, really. Here's my function. I'm given d theta dt, and I want dr dt. So I'm going to take the derivative of both sides with respect to t. So the derivative with respect to t of r is 1 dr dt. implicit differentiation. The derivative of 3 is 0, and then we need the derivative of this with respect to t. Well, first I'm going to take the derivative with respect to theta, and then I'll multiply by d theta dt, implicit differentiation. So the derivative with respect to theta is a negative 4 cosine of 2 theta, and then we'll multiply that by d theta dt. Okay? All right, and now we just have to put in pi over 6. So at pi over 6, say what we're doing. So at theta equals pi over 6, drd theta is negative 4 cosine of pi over 3 times 3 for d theta dt. And that would be a safe stop spot, so I'm just going to stop there. This was just worth 2 points too. 1 point for what they say is the chain rule with respect to t. That was right here. That was the chain rule with respect to t. And then 1 point for the answer. Okay. Got one more problem to do for an example, and that was the problem from 2009. Okay, 2009. This was on Form B of the exam. I'm not sure if they always have a Form B of the exam, or if it was just some years. I know that in some years they do. But anyway, this was 2009 Form B. It was number 4, no calculator. All right, so no calculator on this one. Turn that guy off. Okay. The graph of the polar curve r is equal to 1 minus 2 cosine theta for theta between 0 to pi is shown. So there's only one curve shown, okay, and it's a piece of a little limacon with a loop, because that's a limacon with a loop, right? It's shown for 0 to pi, so keep in mind something. When theta is 0, over here, let's find where we're beginning. When theta is 0, if I put 0 in for theta, cosine of 0 is 1, and I'll have 1 minus 2. So when theta is 0, r is a negative 1. So when you're graphing that, right, here's theta is 0, we go on the other side of the origin to negative 1. So this is where we're starting. That is theta equals 0. Okay? And it describes S, the shaded region here. Part A, we're supposed to write an integral expression for the area of S. I know that my integral will need to start at 0. My question is, where should my integral stop? I need to stop right here. I need to find theta right there. So that's one of my issues here. I need to find that theta value. Well, to find that theta value, we know that at that theta value, r is 0. So if I take my equation and set my equation equal to 0 and solve for theta, I'll have that theta value. So that's my first step here. R is equal to 1 minus 2 cosine theta. I'm going to set that equal to 0 because that's what I want r to equal for that spot. So if I subtract 1 over, then divide by negative 2, I'll have cosine theta is 1/2, right? So what theta value, what's the first theta value after 0? I mean, going from 0, what's the first theta value that makes cosine 1/2? We need to know that that is pi over 3. So this theta value right here is pi over 3. This theta value is theta equals 0. Okay? So our expression for the area of S will be the integral from 0 to pi over 3, of 1/2 of r squared. Since there's only one r in this equation, you could just put r squared here, and that's fine. Or you can write out what r is, and that's fine too. They mean the exact same thing. So that would give us full credit because it just says to write the integral expression. Let me see how much that was worth, you guys. this was worth 2 points. 1 point for the limits and constant. Remember, the constant is the 1/2, and then 1 point for the rest of the integrand. Okay, part B. Write expressions for dx d theta and dy d theta in terms of theta. So they're not asking us to find the slope, they're just asking us to find the top and the bottom of the slope. Okay? All right, so I'm going to start here with dx d theta. For dx d theta, I know x is equal to r cosine theta, right? So for us, r is 1 minus 2 cosine theta. So dx d theta will be, just a little product rule here, so I start with my parentheses and take that derivative. The derivative of this will be a positive 2 sine theta, right? Positive 2 sine theta. Multiply it by that cosine theta, left alone, plus, and now I leave the parentheses alone, and multiply by the derivative of cosine theta. The derivative of cosine theta is negative sine theta, so if I want to, I can make that a minus and make that a sine theta, or I could have just multiplied by negative sine theta there. That would have been fine as well. Okay? Now for dy d theta. Well, y is equal to r sine theta, so y is equal to 1 minus 2 cosine theta times sine theta. And now the derivative with respect to theta will be the derivative of that parentheses, which is still 2 sine theta, times sine theta, left alone, plus, now I'm going to leave this parentheses alone, and multiply by the derivative of sine, which is cosine theta. So those are my expressions for dx d theta and dy d theta in terms of theta, because there's all thetas here. This was worth, they counted this worth 4 points. 1 point for uses x is equal to r cosine theta and y is equal to r sine theta. So 1 point for using that. 1 point for drd theta. Drd theta was our 2 sine theta, because that was the derivative of r with respect to theta. Okay? And then 2 points for the answer. Not sure if it was split up into the 2 answers, 1 and 1, or it was either 2 or nothing. Not sure on that. Okay, part C. Write an equation in terms of x and y for the line tangent to the graph of that polar curve when theta is pi over 2. So we're writing the equation of a line. Well, for an equation of a line, I need a point and a slope, right? Let's do the point first. I need the point when x is pi over 2. And I need this in terms of x and y, so I'm going back and using x and y, right? So x is equal to r x is equal to r cosine theta, right? R cosine theta. So r is 1 minus 2 cosine theta, and then cosine theta. So x is r cosine theta. Now I just need to put pi over 2 in for theta, right? So x at pi over 2 will be 1 minus 2 times cosine of pi over 2 is 0. Cosine of pi over 2 is 0. So x at pi over 2 is 0. Y is equal to r sine theta. So y at pi over 2 will be 1 minus 2 times 0 times sine of pi over 2 is 1. So y at pi over 2, the y coordinate is 1. So the point The point is the point 0, 1. Okay? All right. Now for the slope. For the slope. Well, the slope is dy dx. It's always dy dx, right? In polar, that would be dy d theta over dx d theta. And we found both of those above, right? So dy d theta is here. Go ahead and copy that down. And dx d theta is right here. Oops, that was a plus up there, sorry. Okay, and now, so dy dx at pi over 2 will be, alright, sine of pi over 2 is 1, cosine of pi over 2 is 0, right? So this will be 2 times 1 times 1 plus 0 times 1 minus 0. So that's just going to be a 0. Okay. Down here, the cosine of pi over 2 is a 0. So that's going to be 0 minus, this is 0. So we have 1 times 1, right? So that'll be a negative 1 minus 1. So the slope is a negative 2. Our equation of the tangent line then is y minus the y value is equal to the slope times x minus the x value, and we're done. This was worth 3 points. 1 point for the values for x and y. So that would be the point. Okay. 1 point for the expression for dy dx. The expression for dy dx. And then 1 point for the tangent line equation. So that's what you might, type of thing you might see on the polar, apolar FRQ on the AP exam. Now it's time for you guys to go and try the rest of these on your own.